next paper is paper 71D. The title is The Extraction of Site Energy Distributions from Temperature Program Desorption Spectrum. Our authors are Lee Brown, Scott Bishke, R.M. Schimbalkar, B.J. Travis, and David L. Bish. Our speaker is Dr. Lee Brown. He received his B.S. degree in chemical engineering at the University of Notre Dame and his master's and Ph.D. at the University of Delaware, and he's currently with the Los Alamos National Laboratory. Dr. Brown.
Could I have, is that visible? Okay, better. This is in the nature of a progress report, and I apologize for not having preprints, but if anybody wants the paper, the first one on this will be ready, I suspect, in about 4 weeks, and the next one in about 3 months. If anybody of you wishes reprints on this, please just flip me a business card after the talk here. There is an ancient and honorable history of the last 45 years of papers dealing with the extraction of site energy distributions from absorption isotherms, and the results of this have been sort of equivocal. And well, there's some argument and real doubt as to whether you're seeing just noise in the data or whether the things are real. It depends on the system and what you're doing. So what we're trying to do is get something a little better and more definitive. And before we go into the ones where we have non-uniform surfaces, let's take a look at the uniform surface equation, where here you have a typical TPD spectrum. Incidentally, the temperatures, you'll see the energies in this paper are a little higher than normal. That's because of the systems that we've been dealing with. The results are readily usable at lower temperatures and lower energies of absorption. What we've got here, in order to get your parameters A and E, the first developers of this technique recommended peak analysis at different heating rates, but with the advent of good nonlinear regression techniques, it turns out, I mean, you can pick sometimes as many as 100, 500 points off of this. You've got 500 points and 2 unknowns. I mean, that is a real overdetermined system. So you use just nonlinear regression to get your values of A and E. However, if you use this nonlinear regression to get values of A and E, and you happen to have a non-uniform surface, you're going to end up with this being your calculated and this being your experimental, and you are not matching physical reality. So you need to do something to figure out how to handle this non-uniform situation. And so you draw up your equation here. Incidentally, I'm assuming first order desorption here, and we'll talk about different orders in a few minutes. But what you have here, if you have second order, this would be just squared or whatever order you have. Anyway, this is the equation where we have, of course, the surface coverage, the activation energy, and then a site energy distribution where eta of E to E is, of course, the fraction of sites with energies between E and E plus dE. And what you're really trying to look for is get this distribution function, extract this from the equation, and this, of course, is what you have as your experimental data. Now, this is a Fredholm integral equation of the first kind, where we have the g of x and the known kernel here, the unknown distribution. G of x is your experimental data, which may or may not have significant noise. Now, when you try to solve this thing directly, you just end up with hash. That this is actually a pretty good solution if you happen to try to cut down your size of discrete variables. You can easily get overflows on your computer with no problem at all, as I discovered the first time I tried to solve one of these things. And the presently most favored technique on this is something called regularization, developed both in the Soviet Union and the United States, where they essentially use a damping factor to damp out the high-frequency noise. All right, so if you do that, you end up with something like this, where if you have an underdamped solution, you have a fair amount of noise. If you have an overdamped solution, you've lost a lot of information. And if you have the properly damped solution, you will get a good match between your site energy distribution and the experimental and what is there in reality. Unfortunately, in many cases, and this is the real problem with the exacting site energy distributions of absorption isotherms, that you have no criterion to tell you when you've reached the proper degree of damping. But there's a happy coincidence in temperature programmed desorption, and what we have is to illustrate this, we took 4 different SEDs. We have a one peak distribution here. We have a 2-peak, which we call eta 2. We have a 3-peak, which we call eta 3. And I'm sorry that the Maxwellian type of distribution didn't come out all that high, but that's eta 4. And if we take, these are the site energy distributions, and we use these to generate synthetic data, synthetic TPDs, and you take a look at the synthetic TPDs we got, the 1-peak exhibits 1 peak, the 2-peak exhibits 2 peaks, the 3 peaks exhibits 3 peaks, and the Maxwellian exhibits sort of a Maxwellian shaped TPD spectrum. And this turns out to be true for almost all TPDs. There are, of course, times when if you have your peaks too close together, you won't pick them up in a TPD spectrum, but it turns out that the distinguishing thing is somewhat less in most circumstances than 1 kcal, quarter of a kjoule, which is really a pretty small. So you can distinguish peaks, well, I don't know, about 800 calories, 500 calories, depending on the situation, which means that you now have a criterion for telling where to stop damping your material. And when you start getting more peaks in your site energy distribution than you have in your TPD spectrum, you'd better quit. And you stop damping there. And as a result, if you do this, and what we did in the next slide is try to recalculate from these data. We tried to recalculate our TPD spectrum. We did it. You can see, if you're up real close, you can see the dotted lines lie on the solid lines almost exactly. There are just small bits here. You get just excellent agreement. However, there is a problem here. And this problem was what kept this thing from being published about 3 years ago.
Selective.
That in order to do this, you must know your pre-exponential factor. In the Arrhenius expression A to the minus E over RT, you've got to know A in order to do this. Most of the time, you don't know A. There are methods of getting it. There are a great deal of work. I recommend very highly the paper in Surface Science last spring. Lanny Schmidt was one of the co-authors. I think Edmund Seebauer was the first author, so if you want to look up a first-rate literature review, I recommend it highly. But anyway, if you know the pre-exponential factor, you can get the site energy distribution with a great deal of accuracy just by using regularization to extract to solve the associated Fredholm equation. If, however, you do not know your pre-exponential factor and you use the wrong one, you'll get a site energy distribution of the correct shape with the correct characteristics, but it might be off by 100 kcals or so as far as absolute value. And this is not really a desirable situation. So we are forced then to go to something else. And if you happen to carry this out at different heating rates, you do get different information. And we tried, you notice I made a comment that you don't want to use, there's no real point in using peak analysis to get your values of A and E when you have a uniform surface. But we tried using the TPD spectra in a gross way in their nature for that, and we failed. So we had to go to peak analysis. And it turns out, if you take a look at peak analysis for the uniform surface case, what you end up doing is taking the second derivative, the peak, the second derivative equals 0. You have here an equation where you know the temperature of the peak, you know beta, your heating rate. The only things you don't know are the desorption energy and your pre-exponential factor. So what you need in theory is 2 different peaks, and you can solve this nonlinear equation for your values of A and E, and of course the more peaks you have, the greater precision you can get out of this. All right, if you take a look at this situation for the non-uniform surface, things do not look nearly as good. You carry this thing through, and you find out that at the peak, the second derivative here, which was this expression, you set equal to 0, and it looks like a real mess. I took a look at this, quite some time ago, said there was no hope in peak analysis, and spent, an incredible amount of time trying to reduce this equation to something simpler which I could use. And then the postdoc who was working on this thing, Rajiv Chamberkar, took a look at this thing and said, well, why not just try the peak analysis for the uniform surface case and see what happens? Do you get a straight line? Now, this isn't a particularly good plot, but the idea is, yes, you do get excellent straight lines. This is computer-generated data. If you want to take a look at some experimental data, this is the absorption of CO from graphite, chemisorphed CO from graphite, and you see, again, you get, this is over a heating rate factor of 30. The data are that of Jerry Britton from the University of Colorado a number of years ago. And again, you get really an excellent straight line at this. All right, if you get a straight line, it means that you can extrapolate this, again, assuming that you've had something equivalent to the uniform surface, and you can extract values, some sort of average E, but you also get your pre-exponential factor out of this. Are these pre-exponential factors, how do they relate to what is really there? And it turns out, if you take a look at here, the truly pre-exponential factor we used in these computer simulations was 10 to the 13th inverse seconds. We got here 3 values for 3 different situations that we tried. One was 2.7 times 10 to the 13th, another was 2.4 times 10 to the 13th, and the other was 1.1 times 10 to the 14th, roughly within an order of magnitude. For people who have played around with this, you know that within an order of magnitude for the pre-exponential factor is usually adequate. You'd like better, but off by a factor of 3 is very good. You'd like better, but this is the present situation which we've got. For all the situations that we have considered, we have come to the fact that we can present this, or that we can acquire a pre-exponential factor within approximately an order of magnitude. Okay, where do we go from here? First of all, we want to see, why does this work? I mean, what we essentially did was take this thing in brackets and set it equal to 0, which meant that if you're, and that's only at one point, and if you take a look and say, gee, why should this equal 0? Why should this factor be equal to 0 at that point? And what you see is that if you've got a very sharp peak, for instance, if eta v was a delta function, it would be equal to 0 at every place outside of E. Well, it isn't equal to that, but it does drop off. So that decreases the thing. It is also true that your d theta at lower and higher energies is not particularly large. So what you've got is, while not a delta function, or this is not, this integral is equal to 0 at the peak. It is also true that these factors outside of the particular peak value of E sub d of your energy of desorption can be very small. And that's the reason that using this, you end up with an approximate value of your value of A. All right, where do we go from here? The next step is to see how good we can really get our pre-exponential factor by taking the pre-exponential factor we get from the peak analysis, extracting a site energy distribution, and then searching this area here with site energy distributions for values of A within that region. If we can get, for the different peaks, the same etas for, and the same values of A for, say, 3 different peaks, we shall say that, yes, we can do much better than our order of magnitude in getting A. Once we do that, and I think this is going to happen, and it will be true. Incidentally, as I say, this is a progress report. We finally figured this thing out about 4 weeks ago, that we could pull A out of it. That was sort of down to the wire on this one. Especially since I promised it last March in my abstract. The next step on this, assuming that we can get better precision in our value of the pre-exponential factor, which I'm really confident about, the next value is, and we've got some ideas on how to proceed from this, is how to analyze the situation where A is not a constant, but rather where A is a function of your site energy. I think we can do that too. There's one other thing that I haven't addressed here, and that's the situation, as I say, up until now we have just talked about the first order situation. And in order to get this thing down right, you must know the order of your desorption, whether it's first order, second order, half order, 1.5, anyway, whatever it is. And in order to do this, you cannot extract it from the site energy distribution data. You might be able to do it by different heating rates, but I really doubt that. What I suggest is done in this situation is that you get some uniform surfaces of the same material, of your same metal, and see what happens with the uniform surface, because with the uniform surface, it's very easy to distinguish between different orders. The trouble with if you assume one order, you're just going to get a different SED. Another way of doing this is to start out, and this is not as unequivocal, but you can still do it, is to start out with different surface coverages. So those are the techniques you need to do to get the order. In order to use our technique for getting the site energy distribution, you must know the order, and you must know the pre-exponential factor. What we've done here is to show, yes, you can get a reasonable value of the pre-exponential factor. Next step is to see how we can get the pre-exponential factor that's dependent on site energy, and after that, the next step is to be able to pull out the true temperature program desorption spectra when transport affects it. But anyway, that's our program. Thank you very much.
We've got time for several questions. Greg?
I take it from your title and interest in site energy distributions that you're interested in applying this technique to real high surface area catalysts?
Oh yes.
In that case, my comment is that in the last 10 years or so, there have been a number of groups that have presented analysis of temperature program desorption from high surface area materials, and they've shown very clearly that transport phenomena are in fact the dominating factor in determining the physical content of a TPD spectrum. I wonder if you'd care to comment, or I would suggest perhaps that be the very next thing you take a look at.
Well, what we have here, and you're quite correct. I mean, the transport effects really, as I pointed out, that's the next step. It's an inversion problem. We have some ideas on how to attack this particular problem of pulling the TPD, what you might call the true TPD spectrum. I mean, this problem has already been attacked in some things. I think Gort at, where is he? Penn? And I know Jim Schwartz at Syracuse have both published papers that have some, deal with some aspects of it, but to my knowledge, the problem has not been satisfactorily resolved yet.